Maybe today the talk will be very theoretic, I don't know. But
some mix.
But look at the title at least. The optimal transport and nonlinear differential geometry is very abstract, but the model for data analysis is very hard nowadays. Let us welcome Jim.
Okay, so thank you very much for the invitation. I'm having a really great time in Taiwan. This is my second visit, but I'm enjoying it very much. And so the title is actually slightly different from what I'm really going to be talking about, technically. So I don't know if how team maybe has not communicated this. So what I'm going to be talking about today mainly is the optimal transport problem and some numerical approaches to solving the optimal transport problem. So there are a lot of very recent developments in machine learning and manifold learning and such data sciences where one tries to apply optimal transport theory. And so it's very important that we have real effective tools to be able to numerically calculate solutions to this problem. But the problem is the optimal transport problem originally is very highly kind of nonlinear and generally very sensitive to small errors, that kind of stuff. And it has been relatively recent that good, rigorous numerical methods have been developed. So I want to talk a little bit about that. So what I'll do is I want to start by just introducing the background. I'm not going to assume any prior knowledge about this optimal transport problem. So I will introduce all of the definitions from the basics, and I will state certain theoretical results without really proving them, because that in itself would be just an entire course. So I'll skip those and give references where appropriate. And then I will talk about a couple of numerical methods. And again, you know, I won't go super into the details of the proofs, but I'll try to give a flavor of what kind of analysis goes into there. Okay, great. So, start here. So the optimal transport problem. It's also known as the Monge-Kantorovich problem. And so let me start with just the very kind of abstract setup for this problem. So what you have are x and y. These are generally complete metric spaces. Okay. And then you have two probability measures. So mu, this is a Borel probability measure on the first space x, and nu, this is a Borel probability measure on the second space y. And then you have one more ingredient, which is c, so the lowercase c. This is a function defined on the product, x cross y, and usually real valued, often non-negative, but just generally real valued, or sometimes even extended real valued, let's say. And this should just be a Borel measurable function. Okay? So this is usually called the cost function. Okay, so then what exactly is the optimal transport problem? So the original optimal transport problem is due to Monge here. So it's often called the Monge problem. So what is the Monge problem? We want to find a map, call it T. So T should be a map from x to y that is measurable, so Borel. And we wanted to minimize a certain functional. So this is optimal transport. So it should be a minimizer, so argmin, of the following functional. So the integral of c of x, and let's call this t tilde x d mu x. Okay, and then what should this selection of t's be? Well, this should be over the class of t which pushes mu forward to nu. Okay? So I remind you this notation of push forward measure is defined by the following. So if t tilde is a map from x to y, then the push forward of mu is a measure on y. And we just take for any set, for any Borel set E. Right, so one takes the inverse image under this map of the set. This is a subset of X, and it's Borel, and you just evaluated the measure under mu. Okay. Okay, so let me try to give maybe a heuristic idea of what this problem is modeling. So you can think of mu as kind of something like a pile of dirt here, right? And then nu is a hole. And then you assume that they have the same total mass. And then what you want to do is you want to take the dirt and you want to move it over and you want to fill up the hole. And so nothing is free. So there's some cost. So if I move 1 kilogram, let's say, 1 unit of mass from a location x to a location y, this costs me something. So maybe it's money, maybe it's energy if I'm talking about some kind of physical problem, but there's some point-wise cost per unit mass. And what this depends on is the location I start and the location I end up. Right? So then if t tilde pushes mu forward to nu, this means that t tilde moves all of the dirt and then it fills the hole, right? Because it's pushing all of this into here. And then this cost functional this is exactly the total cost of moving everything. So what one does is, well, if it costs some amount of money, let's say, then you want to minimize the cost, right? So try to figure out the cheapest way to do this. Okay. Now, you can guess, and by the way, so you can generally call such a T is called a Monge solution. So now you may wonder, where is this Kantorovich coming in? And to look at this, you first want to realize that this particular formulation, right, so what this is saying is that you must find a map, T, which is single valued, at least mu almost everywhere. Right? Because otherwise it doesn't really make sense to push forward under such a mapping. Right? But you can easily think of some examples where maybe there just isn't any map to begin with that satisfies this push forward condition. Right? So if I say mu is just equal to a delta, and nu is, let's say, a sum of two different deltas, right? Then immediately there's nothing. There's no map T that pushes mu forward to nu. Because on the support of this measure, you were forced to split some stuff. So you end up with a problem, which is an optimization problem over an empty constraint set, which is absolutely no good. Right? So you can see there's some issues there. Another thing, so this problem, this objective functional is very, very nonlinear, right? Depending on what this cost function C is, even for some relatively reasonable things, like suppose you're in Euclidean space and maybe this is simply the Euclidean distance to some power, right? Even then, this is a very, very nonlinear problem, right? Does not really look like it has any kind of convexity. In fact, the constraint set itself is not convex, right? So this has very bad properties. You're minimizing a very nonlinear thing over a set that's not convex, which maybe even is empty. So there are a lot of issues with this. Okay? And so Monge originally formulated this problem in 1781. Okay? So of course, back in this day and age, there wasn't even this language of measure theory until Lebesgue came and actually established it. So the sort of formulation was already not very rigorous. But you can see that there were, even if you made this rigorous, there were many, many difficulties and there were many obstacles. And it turns out that solving this, so existence, even for a very specific case, did not come until 1991. And this was due to Renyi. So it was a very, very long time until solvability of this Monge problem was established. So in the meantime, Kantorovich came along, and he decided that maybe one could think of a relaxation of this problem. Okay. And it turns out this was a very good idea. So let me, oops, sorry, I keep hitting this. So let me explain what this Kantorovich problem is. So Kantorovich, he was an economist in the Soviet Union, and he worked on this problem in sort of the 1940s to the 1950s. And so he was interested in how to optimally distribute resources among different locations in the country, right? So maybe they have some railways or things, and then so they want to, so this was in the Soviet Union, so this was back in the kind of communist era. So they have some centrally controlled resources that they want to distribute using their network. So how can they do that optimally? That was the kind of thing he was working on. So instead of looking at mappings that push one measure forward to another, Kantorovich decided to look at the following set. So let's call this pi, capital Pi, mu, nu. So this is a collection of probability measures, we'll call them gamma, on the product. Okay? And then this should have the properties that, so if I say pi x, actually let me say projection. So projection onto x. If I push, so this is a map from the product to x, right? So I push this measure forward, this gives me a measure on x. I want this to equal this measure mu. And then I want this projection onto the second space to equal this measure nu. So in other words, the space of probability measures where the left marginal is equal to mu and the right marginal is equal to nu. So one way you can think about this is pi, it can, gamma. Gamma can split mass anywhere. Right. So then the Kantorovich problem is to find a gamma which minimizes this functional. So I integrate over the product now, just the cost function against some measure, let's call it gamma tilde, And the restriction is that gamma tilde should be in this set. So the right marginal should be mu, left marginal should be nu. So this is much nicer. So why is that? First thing, right, it's immediate to see that if I just take this tensor product, that's always contained in this objective set. Right? So I never have this problem where the constraint set is empty. Okay. Second thing, so if I call this functional, let's call it C. Right, this is linear. Right. And then third thing, so it turns out that this set is convex plus it's compact. So when I say compact, what do I mean? This is with respect to the weak convergence. Right. So recall that we say a sequence of measures weakly converges to a measure gamma if it converges in duality with continuous bounded functions. So in particular, right, so say that C is a continuous bounded function, right, then so you can use this to immediately prove that there exist minimizers of this Kantorovich problem. Okay, so this is a standard argument using just the direct method in the calculus variations. You take a minimizing sequence, you take a subsequence using this compactness, and then use the continuity in the weak sense to just get to the minimizing value. And by the way, this compactness, it follows from what is called Prokhorov's theorem. Okay, so there's a standard theorem on probability measures, Bro probability measures, that gives some kind of compactness with respect to this weak topology. Okay? So this is a nice problem. Sorry, maybe I shouldn't put this up too high. Is this okay? Okay. So why do I say this is a relaxation of the Monge problem? Well, if I had a map T that pushes forward mu to nu, then I can think of the following measure. So I can take the identity map. So this is the identity map on X. And then crossed with this T. So this becomes a map from X to X cross T, right? And then I can push forward the measure mu. And I can easily see this thing will satisfy the left and right marginal conditions. Right? Yeah, question? So continuous bounded functions. And so here, right, if I take the integral over the product against this measure, right, so let's put it this way, X, Y. So it's just a matter of untangling definitions, but this becomes the original functional that you are trying to minimize in the Monge case. So it's appropriate to call this Kantorovich problem a relaxation of the Monge problem. Okay. So Kantorovich sort of shifted attention to this relaxation, and he actually got a Nobel Prize in economics for his work related to this. But that's not all. So Kantorovich had another very important contribution, which is the notion of duality. So this dual problem, it's very common, right, in optimization that you have some kind of primal problem that is, say, a minimization, and then that's dual to a problem which is a maximization over, say, the dual space of the constraint set of the original. And so this Lagrangian duality. And it turns out there's a notion of that for this optimal transport problem, or at least for this Kantorovich problem. And actually, exploiting that duality is a very key and important ingredient of Brenier's proof here to get the existence of the Monge solution. So basically, the dual problem is over a nicer collection of things. The objective, functional, and the constraint set is nicer. So you can more easily get existence there. And then by using the fact that there's some kind of relation between the dual problem and the original problem, you can say things about minimizers of the original problem. So what exactly is this dual problem? So let me just make sure I'm using consistent notation here. So let me define the following set. So I'll call this phi c. So these are pairs of functions. So let's just say they're one functions. So phi is a function on x, psi is a function on y. And they should satisfy this following inequality. So minus phi at x minus psi at y should be less than or equal to the cost function at xy. And this should hold for let's say mu tensor nu almost every xy. Okay. Then let me define this functional j of a pair phi psi. So this is simply minus the integral phi over x against mu minus the integral of psi over y against nu. So the Kantorovich duality theorem is, if I take the minimizer, right, so let's say gamma tilde, so I take the Kantorovich problem, right, this is equivalent, so the minimum value is equal to taking a supremum of this functional j over pairs in this constraint set. Okay. And so here, let's say, this holds in kind of more generality, but let's say for now, if x and y, these are compact, and c is a continuous function. Okay. This holds in more generality, but for now, let's say that. And actually, I can get away with restricting this to continuous functions here. So I don't have to look at L1 necessarily. Okay.
So the right hand is soup, not maximum.
Yes, it's a soup, and if you add a little more, you can say it's a max. So for example, let's say if C, so let's say if you are in Rn, and C is, let's say, uniformly Lipschitz. Oops. Then soup is actually a max. So if you add a little bit more, you can get something. Now, there's a very natural economics interpretation of this dual problem. Okay? And so let me just very quickly try to explain this. So say you own some company and you're manufacturing goods, right? So that's your factories are located in the space X. You have these warehouses, and your warehouses are located in the space Y. And what you do is you make your product, and maybe say you make one kind of product, like flour or something. And you have to move it after each cycle to the store, right? And so you calculate, okay, how much does it take to move 1 kilogram of flour from your factory at X to your warehouse at Y? That's exactly your cost function. So this side is you know how much it's going to cost you to move all that stuff. You try to make it cheapest, right? So what is this side? Well, so say that some company comes to you like FedEx, and they say, okay, we will take care of your shipping. What are we going to do? We're going to charge you some amount to pick up 1 kilogram at X, and we'll charge you another amount to drop it off at a location Y. So how much do they charge you? They say, we'll charge you this amount. This is your pickup fee. And then this amount minus psi, this is your drop-off fee. Of course, if it's too expensive, you'll never want to do it. So they guarantee it's cheaper. Right? So if you send 1 unit of stuff from X to Y yourself, they'll say it's more expensive than if you let them take care of it. So you say, okay, great, it's cheaper, so we'll let you do it. And then what this duality problem says is if they're very, very clever about how to charge these fees, they can make you pay the same amount anyway. So that's this sort of economic interpretation. But it turns out this dual problem is very useful to exploit in numerics. Okay? So I want to, let me make sure that I have nothing else to say for this portion. Right, so let me say something very, very brief about how you might go about proving this kind of thing. So there are a few ways to do it. One relatively kind of maybe classical way you can do it is if you view this minimization, right? So this is a minimization of a convex functional over a convex set. So you can rewrite this as an unconstrained minimization just over the class of all Borel measures. And then you add some function which is an indicator function. So the function will be plus infinity if your measure is not in here, right? So then when you minimize, it's the same as doing the constrained version. But then you can take that function and you can rewrite that as a maximum of some expression. Okay? And this maximum will involve the dual space, or rather the space that's dual, whose dual is the space of measures, which is the space of functions. Okay? So then you have an expression, so this becomes something that looks like a min, max of some stuff, and then you can, in this particular case, you can rigorously interchange the max and min. And then you take this portion, and if you run through a similar argument, so part of this becomes this objective functional, and part of it becomes this constraint. Okay? So that's one way, for example, that you can prove this. That's a relatively standard way to do it in this theory of Lagrangian duality. Okay, so that's sort of enough for this. And, oops. Right. So, one more thing I want to mention before I get into some of this numeric stuff is the following. So, on the surface, this dual problem looks kind of not very nice, right? Because you just have pairs of functions that satisfy some kind of inequality. But maybe that's not so much structure. And it turns out that if you look at this dual problem carefully, you can restrict your class, right? So at first it was L1 functions, you can restrict it to continuous functions, but you can actually restrict it to a class that is even better structure. And that's where you get some kind of compactness, for example, so you can get that's a maximum instead of a soup. So notice, okay, if I have a pair B and C, which is in this set, right? Then I can define the following. So we call this psi, and this is called the C star transform. So this is going to be a function on X. And I'll define this to be the supremum over Y of this quantity, minus Cxy minus phi of Y, psi of Y. And then I can define this double transform. So I transform psi, and then I transform it again. So this will be a function on Y. And I do basically the same thing, but in X. So then, first off, right, both, So both the pairs psi, C star, psi, and the pair psi, C star, psi, C star, C, these satisfy this pointwise condition. Because these are the original function pairs satisfied the inequality. So this is a quick exercise. And if I take J of the original pair, well, if I replace phi by this guy, the value will increase. And likewise, if I replace psi by this double transform, the value will increase again. So since I'm trying to maximize this functional, right, I might as well just start with only pairs that are these dual transforms of each other. And it turns out that such pairs will have a much, much nicer property. And so here's the key thing that you want to keep in mind. There's a canonical example, which is the case where x and y are an Rn, okay? And then the cost function, let's say these are bounded or compact. And then the cost function is minus the inner product. Okay. So if you mess with this a little bit, you can see that this is equivalent to taking x minus y squared over 2. Okay. So it's not an unnatural cost to think about. So in this case, so the C star transform, this is equal to Lagrange transform. Right, and so this double transform is the convex envelope. So in that particular case, it says that in the dual problem, you're allowed to replace your pairs with conjugate dual convex pairs. And so now you can see that these are much, much, much nicer functions.
The definition of the star, price star, C star.
Yes.
You only use one function, right?
Yes.
You just use one function.
Right. Yeah. Yeah. So you can just take one function and then you just transform it twice. And as long as the original pair satisfied this inequality, you'll get something that improves the dual functional. So one way you can think about this is, so this function, psi C transform, right? This is a function that's built on top of an envelope of functions that look like minus the cost function at different points. And then essentially the optimal map is going to be one that takes this point x and it should map it to this corresponding y. That's what the optimal map will be. So this is a very kind of key observation. And this is what Brenier exploited to get the existence for the Monge problem in exactly this case. Okay. So now let me start moving into the numerics. So where are the numerics, right? Because I'm assuming most of you are here for that specifically. So let me start with, since I just introduced this duality, a family which is often known as dual methods. Okay? And so I'll start with the simplest case, which is really what's called the assignment problem. It's a common problem in computer science, right? So this is when I'm transporting two empirical measures. So mu is sum equals 1 to n. All the weights are 1 over n. And there's some family of deltas. And nu is also a discrete measure, so it has the same number of points. And again, all of the weights are the same. And now, really, the cost function, well, I can represent this by an n by n matrix, right? Because I only care about the points at the corresponding x's and y's. So then what am I really doing? Okay, so basically the optimal transport problem is the following. I want to find a matrix, let's call it pi, let's call it gamma, j. Okay, so this is what is called a bistochastic matrix, right? In other words, if I sum the rows, there should be 1. If I sum the columns, there should be 1. And I want to find a bistochastic matrix that minimizes the following linear functional, which is simply, so I'll call this C of gamma, again, suggestively, so this is the sum over I and j, Cij, gamma ij. Right? So this is literally just the Kantorovich problem, right? So really this is Kantorovich. In this discrete setting. So, okay, well, it turns out that in this empirical case, you always have a Monge problem. Okay? So there's this Birkhoff-von Neumann ergodic theorem, Birkhoff-von Neumann theorem. So what this says is the extremal points of this set of bistochastic matrices is exactly equal to the set of permutation matrices. And I recall, so a permutation matrix, remember, it says there's exactly 1 number 1, oops, in each row and each column. And then zeros elsewhere. So in other words, you can think of this as building an assignment between points xi and yj with no splitting. So one point here is exactly matched with one point here under a permutation matrix. So then obviously this thing is linear in here, right? And then the set of bistochastic matrices is a convex set. So a linear function always takes a minimum value somewhere at an extremal point. So you know that there's at least one permutation matrix that's a minimizer. Then, so there are some issues, right? So depending on the slope, quote unquote, that this cost matrix defines, you may have your polytope looks like this, and then the level sets of that function may exactly overlap a face or something. So you may have permutation matrices, but you may have things in between that are not, right? And these could all be minimizers. But there's at least one, which is a permutation matrix. Okay. So then you might say, oh, fine. Well, we know that these things exist, so why don't you just take all of the vertices, these are the extremal points, you plug them in, and you try to minimize. That's a bad idea, because there's too many extremal points. Basically, there's on the order of n factorial extremal points. So this is too many to check. Right? Very bad. Way too many. So the naive hope is quickly out of reach. If you have, say, 70 points, then it's impossible to do. And in sort of the data world, right, 70 points is kind of nothing. You want to talk about millions and millions, if possible. So is there a more clever way? Okay. So this idea of just checking the extremal points uses nothing about this duality. Right? All you're doing is a very brute force thing. You're saying, minimize this. Well, we take a smaller set of things, just plug them all in. So you're not looking at this dual problem at all. And it turns out that there are a number of methods you can use where if you exploit this dual structure, you can get way better performance. So you can take something that looks like n factorial, and then you can change it into some things that run in polynomial order in n. Okay? So one particular example that I'll maybe go through in a bit more detail is called the auction algorithm. So there are other duality methods. And so, of course, you might say, well, if you stare at this hard enough, this is really just a linear programming problem, right? I mean, it's a linear function, and then you just kind of add a finite number of linear constraints. So this is a linear programming problem. So there are many famous things, right? So you can use the simplex method. Or there's something called the Hungarian method. But the one I'll talk about today is specifically called the auction algorithm. Okay. And so this is originally proposed by Bertsekas in 1981. And so his is originally, a much more linear programming kind of, not approach, but using the language of linear programming specifically. So if you want something that goes into a bit more detail and specifically uses this optimal transport language, let me give you a reference. So there is a paper due to Conton. There you go. And so it's called, let's see, a comparison of two dual methods. Blah. And this is, I believe, 2013. So if you want some more of the details in the supplemental transport language, I recommend taking a look here. Okay, so let me very quickly try to explain this auction algorithm and then give a few results about the kind of performance and maybe give some heuristic explanation about what's going on here. Okay, so first of all, let's all assume that all of these entries in the cost matrix are positive. That's easy. You can just add a fixed constant to all of them. There's only a finite number, so that doesn't hurt anything. Okay, and so what is the algorithm? So I have three things. So I have a set S. So this is going to be a subset of X, of the points X. I'll have a map T, which is defined on this subset into Y. And this will always be injective. And then I have a vector, which I'll call psi, Rn. So this is something that I'll call the price vector. So I'll explain why in a second. So what do you do? So at the very beginning, well, oh, sorry, there's one more thing. I'll fix a parameter epsilon, which is some positive number. Okay. So what do I do? Well, at the very beginning, this set S is empty, and then this price vector is just all zeros. Okay. Then what do I do? So I pick any point, let's call it xi. This is something in X, but which is not in S. Okay. And then I calculate the following two things. Let me say yj sub 1. Okay, so what is this? This is, I need to maximize over j's, and I look at this quantity, minus c ij minus psi j. Okay, so this I is the same I as here. Okay, now I want to maximize this over all possible j's. And then I take another y, so I'll call this yj2. And so this is the same thing, but I will remove this j1. Okay, so I have two different objects in Y. Okay. So now, if I look at this first object, yji, if yji is equal to tx, let's say I prime, and there's some xi prime in S, what do? I just remove this xi prime from this set. And then otherwise, I add this element, xi, to S, right? I picked something that wasn't in S, so I add it to S, and I set this yj to be equal to t of this xi. Now I have to update the price vector corresponding to this object. So I'll set psi, the j1 component, to the following value. So this is minus Cij1 plus Cij2 plus psi j2 plus epsilon. Then you repeat. Okay, so let me read this up here. So, okay, right now this looks like just a bunch of random stuff, right? A bunch of random steps that you do and then blah, 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 blah. But there's actually a very nice interpretation of this in terms of this dual problem. And there's a reason why this is called the auction algorithm, because this is modeling some kind of real-life auction. Okay, so let me try to give a heuristic explanation. So the set X, it's the set of buyers. The set Y, this is the set of items for sale. Okay. And then psi j is exactly the current price of the jth item. And then what is this Cij? So minus Cij. This is how much the item Yj is worth to the person, the buyer, Xi. Okay? So each person looks at all the items and then they give they assign some kind of intrinsic value. They say, oh, I think this is worth this much. Okay? And so now you have an auction, right? Where basically one rule is that each person Xi gets exactly one item at the end. Okay. So now if you start looking at these sets, or these steps, you can try to understand what's going on. So first of all, this set S, right? These are the people who are winning whatever item. Okay? So if Xi belongs to the set S, that means the person is given a bid, and it's the highest one, and they have that item. So if the auction ended right there, they would just get that item. Okay. And so now what you do is you pick at random, you pick a person who hasn't gotten an actual item yet, right? Someone who's not winning anything, and you let them bid. So what they look at is the following. Well, if you fix a J, right? So this quantity is the ith person thinks the jth object is worth this much, but if they actually win it, they'll have to pay this amount. So this is what can be called the utility of the item. So minus Cij minus psi I, this is what's called the utility of Yj to Xi. If the auction ended right there, they think that thing is worth this much, but they have to pay this much. So that's how much money they make, in some sense. Right? So this is saying that person, the Xi person, they look at all the items, all of them, even the ones that other people have bidded on. And they say, I think this item is worth the most to me right now. And then they say, okay, take the best one away, and the second one. So this is the item that's worth the next most to me right now. So most worth, second most worth. So the person wants to get the thing that's worth the most to them. So they're going to bid for that one. Okay, so if somebody else had already bid for that, well, you're going to beat them. So take it away. Sorry, you got outbid. Okay, so the person is bidding. Okay, they bid exactly for this item. And how do they select the new price? So I can write this new price as the following. Well, this is really the old price, right? And then I will add the following. So minus Cij1 minus the old price, and then minus the next one, plus an epsilon. Okay, so what does this mean? Well, I'm bidding a new price, right? So I have to start with the old price for that item. Okay? And then here, what this is saying is if you pretended like this wasn't here, if the person bid any more, that would cause the price of this thing to become too big. And then they would look and say, oh, actually, I want this thing instead, right? So this increment, adding this amount makes the price of this object exactly so that the thing they're getting right now and then the next best thing are worth the same amount to the person, if that makes sense. Okay? So the person is kind of trying to optimize. But they looked at this thing first. They wanted this thing first, so they'll take this. But they bid so that it's worth the same to them as the second one. But now the auction house is sneaky. The auction house forces you to add a fee. Okay? This epsilon is actually very important. So the person is trying to be clever, but then the auction house is adding a kind of fee separately to the price. So it's forcing it to drive it up. Okay, so then that's one bid, and then you keep going until hopefully everybody has gotten some item that they want the most, okay, in some sense. And then the auction ends, everyone pays whatever amount, and then they get that thing. Good. Okay, so now how much, what exactly is going on with this algorithm? Okay. So you might guess that if you don't have this fee, what could happen is you could have two people who are looking at the same thing. One person says, I want this. They add a little bit. And then the other person says, oh, I want that back. And they add a tiny bit. And then this keeps going forever and ever, where the increment keeps getting smaller and smaller and smaller. And so maybe you have this bidding war that never ends. Okay? That could be bad. And that's exactly why this epsilon, it forces the price to increase by at least this amount. Okay? So if somebody bids on an item, the price has to go up by this amount. So that way you can't do this tiny, tiny, tiny little increments and go forever. And actually, real auction houses do this. So that if you want an item, you have to bid at least this much over the previous price. Otherwise, the auction will never end. Okay. So now, try to analyze this algorithm a little bit. So, let's say the following definition. So if I have a triple, as in this auction algorithm, we say that this triple satisfies epsilon complementary slackness. I would shorten it to epsilon CS. If the following is true, so for any I, then I need to have minus Cxi of Txi minus the price. Okay, and if I add epsilon to this, it should be bigger than all the other ones. And so it's kind of relatively clear if you look at this algorithm that at every step this triple satisfies this condition. So during the auction, S and T and psi always satisfy this condition. So, right, this is basically just an induction argument. So it's simple. Right, so at the very beginning, the set's empty. Yeah, question?
A question about you mentioned about auction in the chapter.
Mhm.
You start with S is the empty set,
Yes.
okay, and then you put xi random x minus x, and then the next step you have xi prime plus some xi prime belong
So-
to S.
yes.
But if you start with S with the empty set.
So this is only if there is some xi. So at the beginning, there's nothing. So you ignore this step. You just do this bid. But then on the next iteration, S contains one thing, right? And so you might pick an xi who decides that they want the same item, right? And if that's the case, the person in the second round is going to outbid the person in the first round. So you take that item away from the previous person and give it to the new person. That's all this line means. And it could be possible that this item's not taken yet. Right? If this is not taken, then the person just bids for it and they get it. So you have to think of this like an auction, but you're not allowed to buy more than one object. If you bid for one object, right, and then you bid for a different, J1 is defined as some item that maximizes this value. And J2 is where you maximize this, but you take away that item.
And in the beginning, you pick xi, what is xi here?
So xi is so you randomly pick that from some person who hasn't bought an item yet. Or who doesn't currently have an item assigned to them. So that's, you pick some random thing. Like maybe you pick the lowest index or something. No. So this is only if there exists an xi prime such that this holds, then do this step. Otherwise, ignore this step. Okay, good. All right, so, so it's not too hard to see that this triple will satisfy this epsilon complementary slackness condition. I mean, at the very beginning, you're starting with the empty set, so it's clear. And then you can just look by how this price vector is changing to do an induction type of argument. So I won't go through the details. But then basically, the main theorem is the following. So the auction algorithm stops, or rather, let me say, it takes at most so there should be n times c over epsilon iteration. So what is the c? C is exactly the maximum value of all of these CIJs. And so basically, let's see. If kappa is defined to be the following, so it should be the minimum value of the difference of any two of the CIJs, so Ci prime, J prime, which is not 0. And you take epsilon to depend on this parameter, so it should be kappa divided by capital N plus 1. Then the thing that you have at the end is actually optimal. So the T at the end of the auction is optimal. So here, I mean in the Cantor-Ridge problem. Okay. And so if you look, each step basically has complexity of order n. So if you do this, the total complexity is big O of n cubed times this c. Okay, if you take this choice. So the total complexity is big O of n cubed, right? So I mean, if we put the actual constants, c kip. Okay. So I won't go through the details on this because I don't think I have a whole lot of time. But first of all, here, right, this fact you can kind of easily see by the fact that every time a bid happens, it forces the price to go up by epsilon. Okay? So think about what happens if there is something that's never been assigned. That means the price is still 0, right? And then you can exploit this fact to say that if some item has been bid on more than this many times, right, then that would give you a contradiction with this epsilon complementary slackness condition. Okay? The price would go up too high if you had that many bids. Okay? And then the second thing is, well, once you look at what you end up with at the very end of the auction algorithm, you will see something like this. So if the auction is ended, then you can look at the following expression. So you sum over I, and you look at the costs of each person and what item they got, right? And then you'll have the following. So this is for any, let's call it T tilde, right, which is a bijection. You'll be able to show that it satisfies the following. Plus n times whatever this complementary slackness parameter was. Okay. But then this thing is exactly n over n plus 1 times kappa, right? Yeah. And so this is strictly less than kappa. Right? So then this is easiest to think. So pretend like all of the costs, all the entries in the matrix were, say, integers, right? So then the only way that this sum could be strictly bigger than this sum is if the difference is 1 or larger, right? And so in general, if this difference is less than kappa, then this sum cannot actually be strictly larger than this sum. So it's at most equal or possibly smaller. Okay? So in particular, this makes this thing optimal. And so you see that the optimality depends on choosing this epsilon in such a way that also depends on the number of points. And so once you do that, it affects the complexity. But anyway, the point is here, these are both numbers that depend on your cost matrix, right? And so this is, in some sense, much better than, much better than n factorial. So you're exploiting this dual structure in order to get a much better performance out of the algorithm. Now, while we are on the, okay, good. So while we're on the topic of these dual methods, I want to say a little bit about the semi-discrete case. So we escape from the discrete problem and talk about the case when the source measure might be absolutely continuous. Okay. Okay. So what do I mean by semi-discrete? So here, I'm going to take this source measure, and I'm going to assume that this is absolutely continuous with respect to the Lebesgue measure. Okay? And let's say compactly supported. But the target measure, nu, this will still be a discrete measure. Okay? But now let me allow it to take different weights, possibly. A finite number of points. So you can view this as a kind of partitioning problem in some sense, right? So say this is your support of mu, right? And say we have a finite number of points. Y1, Y2. And so really what you want to do is you want to take your support and then you want to divide this up in some way into these regions. And then you say that this region is entirely mapping to this point in some optimal way. Okay? And now, if you look at this from the viewpoint of duality, what is going on? So if you remember, I mentioned that you can take your maximizers of this very special form, this kind of dual conjugate form, right? But in the semi-discrete case, what's going on? Well, here, if you remember the objective functional, right, this was defined as this integral. The sum of these integrals. So here, this is a discrete measure. So the only thing that matters in this dual functional is the value of this function at the finite collection of points, y1 through yn. Okay? So I can view this, instead of being a function, this is really a vector still with n entries, right? So really, I'm looking at this vector. And then if I look at this definition, so this is a function on x, but now I can rewrite this as a maximum of a finite number of functions. So this is simply max j running through 1 to n of the following functions, c of x comma yj minus psi of j. Right? So what I really have is the following. I have a finite collection of these functions, right? Each of these is of the form minus c with some yj minus some psi j. And then this transform is just the envelope of this finite collection of functions. Now, it turns out, so I mentioned that there's this theorem due to Brenier on existence of these optimal transport solutions. And one of the results, so one part of the result due to Brenier is that it gives a characterization for when a map that pushes a measure forward to another one is optimal. So if I define the following, right, so go here. So given a vector in Rn, right, I can define the following object. So if I have j between 1 and n, I define this object is called the Lagrange cell. So this is a subset of points in X. And it's the set of points where if I take the transform of this vector, it should be equal to the C, which is defined by this jth point and this jth entry. Right. So in this picture, right, this would be exactly this cell here. So this region here, the Lagrange cell, sorry, corresponding to J, defined by this vector psi. Oops, sorry, this should be J. Okay. So now, if I think about this a little bit, well, I can define the following map. So let me call this thing T. It depends on psi. Okay. T of psi x, I'll declare this to equal y of j if x is in the jth cell. Okay. And now if I add a special condition on C, for example, if I have this canonical case again, right, then the intersection between two different cells this thing has measure 0, right? If I'm looking at two different indices. So the intersection between two cells would be exactly something that's on the boundary here. And that's contained in some kind of lower dimensional hyperspace, so it'll have measure 0. So then, in particular, I'll see that this mapping, if I use that to push forward this measure, I get exactly a discrete measure. The discrete measure is supported on these points. And then what is the weight at each point? This is exactly the measure of the corresponding cell. So for each vector psi, I can use that psi and I can construct a map. That map will push mu forward to a discrete measure. The discrete measure is supported at the right points, but the weight of each point might be different. Okay? And now the magical part is by Brenier's theorem, T psi is always a Monge solution. Okay. So effectively what I'm doing is I'm solving the optimal transport problem, but I have the wrong measure on this side. So maybe my goal should be the following. Find a vector psi such that the weights are the correct thing. So I remember I started with, where did it go? So I started with some collection of weights here. So if I can construct a psi, a vector here, that gives me this. Then I will have found an optimal transport map. It's optimal. It pushes mu forward to this measure, which will actually be the right measure. Okay. So this is kind of the ground idea behind using these duality methods in the semi-discrete case. Okay. So let's see. So I want to just maybe mention a few different ways people have tried this. So one method that people have tried is a very simple iterative method. So what is the idea here? The idea is you cycle through, let's say, the second index all the way up to the last one. And then you increment these by certain amounts. Okay? So what you're doing is you have something like this, right? So let's say this is corresponds to 1, this corresponds to 2, this corresponds to 3. Right? So you leave one of these in place, right? So now I'm looking at this one, so 1 and 3 stay in the same place. And now if I increase psi 2, well, this is minus c y2 minus psi 2. So if I increase psi, this will go down, right? Right, so this has decreased from where it was before. So this changes the size of all of these cells, right? So I move it a little bit and hope that it stays in some threshold. And now I cycle through to the next one, and I decrease this again. Oops. So let's say it was here, and then I cycle through and I decrease it a little bit. Okay? And I keep cycling through this in a very simple-minded way, just lowering each of these a little bit. And so eventually what will happen is this cell is so other cells keep stealing stuff from it, right? So this is always shrinking. And then each time you move one of these, the cell, I think it's the other way around. So each time you move one of these, this thing, more of this is exposed. So this cell is increasing. And each time you move one cell, the size of that one decreases and all the other ones increase. So you keep going through, and then you hope that the structure of the problem is such that it lets you terminate if you're very careful about the increments. Okay? And so there are a number of results that have tried this method for various cost functions. So I believe the oldest one is due to Caffarelli, Kochengian, and Oliker. So this is 1999. So this is for what is called the reflector antenna problem. So the idea is you have a light bulb sitting somewhere, and then you have a mirror, and you want to build the mirror in such a way that you reflect some of the beams of light in certain directions with certain intensities. It turns out you can model that by an optimal transport problem and with a very specific cost. And for that cost, they analyze an algorithm like this and show that it has some kind of finite termination. Okay, so you'd be worried that maybe you keep lowering these and you get into this war where you kind of just keep lowering and you never stop. But actually, if you do it carefully enough, then you can make this algorithm terminate, just like in the auction case, right? The auction case, you force it to increase by a certain amount, so you get termination somewhere. It's a similar kind of idea. And then this was later, so I did this for more general cases. So these are what are called strongly MTW costs. So MTW it stands for Maud-Schrödinger and Wang, and it turns out there's a relation between the optimal transport problem and the Monge-Ampere equation, and this is a condition that you need to get some kind of regularity results for these Monge-Ampere equations. And interestingly enough, the regularity comes into the analysis of these numerical algorithms. Because if you know kind of the folklore, right, so numerical methods for PDEs work better if you know that the solution has some kind of regularity. Right? The solution has singular behavior, then the numerical methods can be slow because they have to somehow account for the singular behavior. And here, you have some kind of regularity, and it lets you say something about the performance. And then more recently, so there's a result due to Vidin and Gutierrez. This is 2017. And this is some generalization of the optimal transport problem itself. So it's something that includes optimal transport problems, but adds an extra layer of nonlinearity. So these are called generated Jacobian equations. Anyway, the exact definition is not important, but just know that it's a generalization that includes all optimal transport problems. And in particular, you don't need this kind of assumption on the regularity and things for their result, which is quite nice. Okay. So all of these, you kind of analyze this, and basically it says something like you terminate in n to the fourth over epsilon steps, where epsilon is equal to the error threshold that you allow. Okay? So it's okay, but not super. Now, another thing you can try to do, right, is to try some kind of Newton method. Right, so if you define the function g of psi as this vector valued function, right, so you just take the volumes of each of these cells. Right, so then your goal is to approximate a root of this vector valued function, g minus beta, and then you use some kind of a Newton type method. So it's kind of the simplest thing you can think of. And so you know that Newton methods, when they work really well. You get linear convergence, maybe local superlinear convergence, all that. But if they don't work, they just totally break, right? And so here, it turns out that by assuming a little bit of stuff, again, in the vein of this type of regularity for this Monge-Ampere equation, you can ensure that the Newton method will work out. So there's a number of results. The first probably attempt goes back to Oliker and Pressner. So this is 1989. Okay. Now this wasn't exactly in the context of optimal transport. This is solving the Monge-Ampere equation. With some kind of Dirichlet boundary conditions. So you can argue that solving some weak form of this Monge-Ampere equation is equivalent to, no, I mean now it's known that it's equivalent to solving an optimal transport kind of problem. But this was the original motivation here. And there's a result by Lapeyre and Rapetti. That's 2005. So this is for optimal transport on the torus. So they do something that really uses the periodic structure here in a very important way. Okay. And then there's some refinements of this. To Sommier, Agay, and Carlier. Oh, no, not Carlier, Codier. Okay, so this is 2015. This is a refinement of this result. There's another result due to Mirabol. 2015. And then finally, myself, Ergo, and Thibert. So this is for these MTW costs. And this is for this Euclidean cost. And there are various things. They have some, they prove some convergence, maybe without convergence rates, or various things. So we were able to get global linear convergence and locally superlinear. If you assume that your source measure has some kind of regularity. So if you assume Hilder continuity of the density of the source measure, you can get some nice results. Okay. So I've been told that some people have tried to implement these in various cases, and they seem to work pretty well. Okay. So that's all I'll say about these duality methods. Now, the last thing I want to talk about are a family of methods that are known as entropic regularization methods. Okay, so I'll go back to the discrete case, but you can apply this in the semi-discrete or even continuous case if you're careful enough. Okay. Okay, so like I mentioned, go back to the discrete case. For now, let's allow something slightly more general. So I'll allow these to have different weights and different numbers of points. So let's say I runs from 1 to m, and j runs from 1 to n. J, right. So these are both probability measures. Sorry, so this should be nu, and this is mu. And let me define this set pi alpha beta. Right, so this takes the place of these bistochastic matrices. So these are m by n matrices. Right, so if you sum the rows, you should get beta j, and if you sum columns, you should get alpha I. Right. Then, of course, our optimal transport problem, right? Is to minimize sum gamma ij, cij over, oops, this collection, right? Right, so as we saw, in the empirical case, right? So we could use this Birkhoff-von Neumann theorem. They said that the vertices are permutations, so there exists at least one nice solution, blah, blah, blah. But in this general case, you can't really say such a thing, right? In fact, you don't even know, right? So this becomes a very difficult combinatorial problem, because you must have some kind of matching up between sums of weights on various sides in order to even have maps that could be permutations here. So this is rather difficult, and the main thing that is kind of a problem is that this part is non-strictly convex. In gamma, right? So the idea behind this entropic regularization is, why don't you try to add a small term to regularize the problem and turn it into something uniformly convex? And then maybe it's easier to get a minimizer. So the idea, so the term that's commonly used is this relative entropy, right? So you define the relative entropy. Okay, so H of gamma is a m by n matrix, right? This is, let's make sure I get the sign right, minus sum over ij of gamma ij of log gamma ij minus 1. So this is if all gamma ij are strictly positive. And this is minus infinity, minus infinity else. Okay. So then you want to think of the following function. So you say, for positive epsilon, you want to define C epsilon of gamma as, well, you have the optimal transport part, minus the relative entropy times this parameter epsilon. Okay. So then you try to minimize this over the set pi alpha beta. Then it's very simple. You just do an explicit calculation. You take this thing, you calculate the Hessian, and this term will be strictly, actually uniformly concave, right? So this thing is uniformly, I guess, epsilon convex, right? So it's easy. You just calculate the Hessian of this relative entropy term. So in particular, there exists a unique minimum, right? Because this is a convex flat set. Right? And oops. So the first thing you might be wondering is how much does this epsilon term throw off the minimization? Well, so there are a number of results that say, oops. So let's call the minimizer of this problem gamma epsilon. Right, so then basically you have that gamma epsilon converges as epsilon goes to 0 to some gamma. Okay, this is a solution of the original optimal transport problem, and it has maximum entropy. So in some sense, you can think of this as being most spread out. Right? Or another way to phrase this is that this will be closest to just the simple tensor product measure. Okay. So it actually picks out something that's unique, even if you have multiple solutions. So this is due to Clemenetti and San Martin. So this is in 1994, and this is the discrete case. And you can actually do an analog of this for continuous measures. And so this proof, so you have to modify this. You say converges, you have this gamma convergence in the continuous case. And this is due to Carlier, Duval, Barre, and Schmitzer. So 2017, and this is for the absolutely continuous case. Okay. Now, good. So in the last 15 minutes, I want to mention, so in this discrete case, there is a very simple algorithm that one can do that seems to work pretty well in practice, which is known as the Sinkhorn algorithm. Okay. So I will talk about that. This is for positive epsilon. So I want to mention that everything from this portion, there's a book, or maybe it's really like a preprint of a book in some sense. It's called Computational Optimal Transport. And this is by Couturi and Perret. And so this material can be found in Chapter 4, at least as far as the version that I have. Okay. So here's the idea. Let me define the following matrix. So Kij is e to the minus Cij over epsilon. Okay. And then I can define this object, which is commonly called the Kullback-Reibler divergence. So KL And so this is simply defined as minus sum ij, gamma ij, log gamma ij over kij, minus, I hope I have the signs right, gamma ij plus kij. Then it's just a matter of calculations, sticking stuff in the log. So you minimize this relative entropy if and only if you minimize this Kullback-Leibler divergence. Right? This is literally just a matter of calculations. Okay? But now, the advantage of this is that if you look at this Kullback-Leibler divergence, you can read off the first order conditions. So you write, the point is, a minimizer of this, you realize that you can write this as a very special factorization of matrices. Okay? So the minimizer can be written in the following way. So gamma ij is equal to ui kij vj for certain vectors u in R, m, v in R, n. So how exactly do you see this? Well, so you add some Lagrange multipliers. Okay, so minimizing this Kullback-Leibler divergence over the collection of pi alpha beta. This is equivalent to minimizing, you can write it this way. It's the same as minimizing Cij gamma j minus this relative entropy, and then you add some terms to enforce the marginal constraints, right? So let's call these f, and you have gamma times the vector that's 1 minus alpha, and another g. This is gamma, so the vector is 1 minus beta. Okay, so these are Lagrange multiplier terms, right? And so if you differentiate this in gamma, and then you set it equal to 0, when you read off the first order conditions, you get exactly something like this. So Cij minus epsilon log of gamma ij minus this fi minus this gj. Right? So if you simply solve for gamma, then you get an expression like this. Right? So u and v are some exponentials of f and g. Okay? So then, what is the nice thing about this? You can equivalently write this in the following way. Gamma is written as the diagonal matrix whose entries are this vector u times k times this diagonal matrix whose entries are this v. And then the point is these, so gamma has to be in alpha beta, right? So you can rewrite this, these two marginal conditions, as the following. So let me use this notation. K v equals alpha, and v dot kt of u equals beta. So this notation means that I take two vectors and I just multiply their components component-wise. So requiring these two is equivalent to having this condition. So then this sinkhorn algorithm, okay, so I'm almost out of time. Is very simply take these two vectors and keep projecting them to have the marginal constraints over and over again. So you start with, let's say, v0 equals the vector that's 1. And then you simply define uk plus 1, right, as a vector, right? So alpha divided by k vk. So this is, again, component-wise division. And then you define v k plus 1 as the component-wise division of this beta by this k transpose u that you got here. So you start with a vector, you construct this thing, so you construct u1, and you construct v1, and you construct u2, just back and forth, back and forth. Very easy, right? All you have to do is do m divisions here and n divisions here, go back and forth. And then you sort of hope for the best. If you do this enough times, then can you get something, right? Once you put these back in this formula, can you get something which is actually a minimizer for this entropy problem? And so the last thing I'll mention, there is a careful analysis of this. And even though this is a very deceptively simple algorithm, it tends to work relatively well. So this is a theorem due to Altschuler, Weed, and Ridley. Okay, so for simplicity, just take the case where you have the same number of points. Then if you take epsilon to be, say, 4 log n divided by tau, for some tau positive, then after a finite number of iterations that can be bounded by, again, we have this maximum of the cost function times log n over tau cube iterations. So whatever thing you end up is, let's call it gamma tilde. Okay, so if you take the optimal transport cost, this is bounded by actually the minimum plus tau. Okay. And because each iteration you're doing, in this case, n equals m, so you're doing n component-wise divisions. So this is really how many calculations? It's n squared times this calculation. So computations. And okay, I have to mention one thing. In theory, you have to add one extra step at the end, because once you do this back and forth, one of these doesn't have the right marginal, right? It doesn't have the correct marginal. So you have to do this rounding thing in order to get it to actually sit inside this set. But if you're careful enough, you can do it without ruining the error too much. And so once you do it, you get this kind of analysis. So anyway, this gives you a method of choosing the sort of maximal entropy solution, right, by taking this epsilon to 0, even in the case where you may have many different optimal transport solutions. So you get the one that's most spread out, which may or may not suit exactly what you want. And there's a rigorous analysis. Okay, so this is sort of a very small collection of numerical methods that are out there, but I tried to pick some ones that are recent and seem to be pretty relevant, and people are actively doing the analysis on those algorithms now. But I don't claim that this is exhaustive or, there are certainly newer, more state-of-the-art things coming out as we speak. But hopefully this will be useful if you want to now do some kind of data analysis applying this optimal transport stuff. Okay, so let me stop here, and thank you very much for your attention.